Hello everyone, this is me Kunal Murke and today I am here with a new topic that is data efficient performance modeling for configurable big data frameworks by reducing the information overlap between the training examples. So let us go with the introduction first. The problem statement of this topic is performance modeling for configurable big data frameworks is challenging due to large number of configuration parameters. The goal is to build data efficient performance models by reducing the amount of training data needed through minimizing the information overlap between the training examples. The context is big data frameworks such as Apache, Spark, and Hadoop offer many configuration parameters, making performance turning complex. So the key challenge is that the gathering of sufficient training data for a machine learning model can be expensive and also time consuming. So the motivation behind this is high dimensionality, where the frameworks like Hadoop and Spark offer many tunable parameters, for example, memory, executors, etc. And the current approach is that it requires large, often redundant datasets for accurate performance modeling. And the goal is to reduce the training dataset while maintaining prediction accuracy by focusing on unique informative examples. Redundant data problem. In traditional performance modeling, many configuration settings result in similar performance outcomes. This redundancy leads to inefficiency when building models as new training examples and add a little value. So the impact on real world applications is in environments where turning is crucial performance, example cloud services, distributed database, and inefficient model hamper quick decision making and resource allocation. So the challenges in the existing approaches are high redundancy. Traditional methods generate redundant data, which makes the modeling process inefficient. Data collection cost, that is, gathering the performance data across numerous configurations is expensive in both time and resources. And there are inefficient models where overlapping examples lead to the less efficient learning and lower model performance. So, what should be the proposed approach? We should go in a systematic manner. First, we need to generate the key idea, then diversity aware sampling, then we need to wait for the expected outcomes, where we require core innovation, information theory basis, and model scalability. Let us look into all these concepts one by one. Key idea is to reduce the overlap by strategically selecting training samples that provide the novel information which has only important data which could be used with the model for the efficient outcomes. And diverse aware sampling, which means introducing of techniques that prioritize selecting diverse training examples. And the other thing is that expected outcomes. Improve data efficiency with fewer examples required for training. So we need to improve the data efficiency with the fewer examples required for the training. So the expected outcome would be better. And we require core innovation where we minimize the number of training examples while maximizing the information gain from each of it. And the next is information theory basis. The strategy leverages principles from information theory to ensure that each example selected adds significant new information in the model, reducing the overlap between the examples. And we have model scalability, where the reduced dataset improves the model scalability for large-scale systems, for applications in the cloud-based systems and edge computing and also high-performance clusters. And the methodology which is used is identify the configuration parameters, diversity aware sampling, model training, and model evaluation. Identifying the configuration parameters includes to define the parameter space for big data frameworks. Diversity aware sampling is we use clusters, active learning, and uncertainty based methods to choose the informative examples. Model training is to build a performance prediction model using machine learning with reduced dataset. And lastly, model evaluation is assessing the model's accuracy, efficiency, and ability to generalize the unseen configurations. So, the diversity-aware sampling techniques are cluster-based sampling, where we group similar configurations and samples from the diverse clusters. Active learning is select the configurations that are predicted to maximize the model's learning potential. And uncertainty-based sampling, where it focuses on examples with high prediction uncertainty to improve the model accuracy. Diverse sampling for robustness, which ensures diversity in the selected examples, enhances model robustness by covering edge cases and uncommon configurations. After that, entropy-based metrics, where the method employs entropy calculations to prioritize the training samples that increase the uncertainty reduction that makes the model learn more efficiently. After that, we have uncertainty sampling, where samples with high uncertainty in their performance prediction are selected to improve the model's accuracy. So, what are the evaluation metrics that have been used? Prediction accuracy. How accurately the model predicts performance metrics like runtime. Data efficiency, where the reduction in the number of training examples is needed. Generalization. Model's ability to predict the unforeseen configurations effectively. And the results. The proposed model achieves significant accuracy with fewer examples, reducing the data size up to X%. Specific metrics from the paper. Efficiency gains. Model built using the proposed approach should significantly reduce in the training data requirements while achieving the similar or better accuracy in the traditional methods. Cross-validation of the results. By testing the model against multiple datasets, the evaluation demonstrates strong generalization capabilities, especially in the unseen configurations. Data reduction rate. It experiments to indicate a potential reduction of training data to be with no loss in the model performance. So at last, conclusion and the future work. Conclusion is that a data efficient performance modeling approach that reduces the number of training examples while maintaining accuracy. Diversity aware sampling ensures the model learns effectively from fewer and more informative examples. The future work is that to extend the approach to other big data frameworks and explore further improvements in sampling techniques like deep learning based diversity measurement. Thank you everyone.